Hello everyone, welcome to the TCS seminar. This week we have Marcin Briański. Marcin is a PhD student at this university, but he has very broad interests and collaborates with a lot of people and has a lot of fascinating papers. Today he will tell us about tripods in directed graphs.
Yes, thank you. Hello all. Today I will speak to you about Erdős-Pósa property of a certain type of structure in directed graphs. So, to begin with, I'd like to quickly tell you what an Erdős-Pósa property is, in case you don't know it. So, it's just a fancy way of saying that there's a functional dependency between packing and hitting certain type of structures in graphs usually, but in our case we'll be mostly thinking about directed graphs. So let's say functional. And it is named so in celebration of a seminal result of Erdős and Pósa in 1965, wherein they proved that any graph G and any we have one of two possible outcomes. The first one is that there are k pairwise vertex disjoint cycles in G, or alternatively, there is a set of vertices of G of size at most O of k, such that G minus the set is a forest. Meaning that this set intersects all cycles, and in the terms above, this outcome corresponds to packing, and the outcome 2 corresponds to hitting. Okay, so this result inspired a lot of future work, a lot of future results, both positive and negative, such as establishing Erdős-Pósa property for A paths, for even cycles, for cycles of a length congruent to 0 mod t. Those are all results that are true, and such negative results such as odd cycles don't have the Erdős-Pósa property. And one result I mentioned here is that minor models of any planar graph have Erdős-Pósa property, which is a result due to Robertson and Seymour in their graph minors project. Okay. And arguably even results before the theorem of Erdős and Pósa fit into this framework, such as Koenig's theorem. That's the duality between, a very tight duality between packing edges and hitting edges in bipartite graphs. So you can translate all of those questions from the world of graphs to other structures. So for example, directed graphs. And arguably, once you go from graphs to directed graphs, this theory becomes much more difficult. So, for example, the original result about cycles, you can just ask, what about directed cycles in directed graphs? Do they have the Erdős-Pósa property? And this was a conjecture due to Younger for over 20 years. And it was eventually proven in, I have it written down. Yeah, in 1996 by Reed, Robertson, Seymour, and Thomas. So fairly big names, I would say, in graph theory. And that indicates that we have a lot, or had a lot weaker grasp of all this directed stuff. But it's not that nothing is known. For example, the result I mentioned about models of planar graphs having Erdős-Pósa property does have its analog in the directed world, where there's following theorem due to Amiri, Babayashi, Kreutzer, and Holland states the following, that the minor models, and here you can think of butterfly minors or topological minors, depending which you want, if you know those terms, of strongly connected digraph. They have the Erdős-Pósa property and this happens if and only if D is a minor of some cylindrical wall. And this may hint you, if you know how to prove the theorem about minor models of planar graphs having Erdős-Pósa property, that the scheme under which you prove this theorem is very, very similar. You apply something called directed grid theorem to argue that if the directed tree width of your host graph is sufficiently high, you trivially pack minor models of D. And if that doesn't happen, you use the composition to guide you in building either a packing or a acting set. But in particular, the assumption of strongly connected is very important in this theorem. If the pattern graph we are looking for is not strongly connected, then the question of having Erdős-Pósa property is already non-trivial for directed acyclic graphs. Yes?
Sorry, maybe I'm missing, but what about this impression for undirected graph? Why does it make sense? Like, do you have such an equivalence for minor models in undirected graph?
Yes. So minor models of a graph of a graph H have Erdős-Pósa property if and only if H is planar. And it's essentially this is a monotone property, so you just show that for K5 and K3 it doesn't hold, and that suffices. Thank you. Okay, so what was I? Okay. So acyclic, yes. So a natural question, at least I think so, is to ask which acyclic patterns have the Erdős-Pósa property. Well, and to my knowledge, prior to this work, there's been only one such result, which should be familiar to most of you. It's the Menger's theorem. Which I will write down the full statement here because I will use it as a setup. So, what does it say? We have a D, which is a directed graph, or D graph. We have two subsets of vertices of this directed graph. And the theorem states that maximum number of pairwise vertex disjoint S to T paths equals the minimum number of vertices such that in D minus X there is no S to T path. Yes. So again, it's a duality between packing and heating, in this case ST paths, and it turns out to be very, very tight, like it's an actual equality. Okay. So what have we proven, actually? Well, to tell you what we have proven, I will need to tell you what a tripod is first. So to do that, we have a very similar setup. We start with a set of distinguished sources and sinks. And we have some directed graph between them. And a tripod consists of taking two distinct sources, let's call them S1 and S2, two direct paths from S1 to some vertex C, and from S2 to the same vertex C that are disjoint, or internally disjoint, and then leaving out to some fixed vertex T. And in this definition, I allow any of those C to be any of S1, S2, T, or any other vertex. So in particular, something that looks like this is also a tripod, and so is something that will look like this. So all these.
The third path from C to T is also vertex disjoint.
Yes, so all those three paths need to be internally vertex disjoint, but any of them can collapse to having no internal vertices, or being completely trivial, so the start is equal to the end. We have managed to prove the following theorem, where by we I mean myself, Majke Hatzel, Karolina Okrasa, and Michał Pilipczuk. The tripods have the Erdős-Pósa property. Which again means that there's a duality between packing and heating tripods in any digraph with a distinguished set of sources and sinks.
Sources and sinks is
S and T.
It's just a name, it's not that sources include sources.
No, this is just some set of vertices. Yes?
In tripods, so your path, they might use many vertices in S. It's not empty, it's not only the endpoints, right?
Yes, but if you use many vertices in S, you can always find a sub-tripod of the type of the bottom. Yes, and that will be strictly smaller tripod. So I think we assume that a tripod contains exactly two vertices of S, and that's that should be equivalent.
It's easier to pack and harder.
Exactly. Yeah. Okay. So let me now give you a quick overview of how this theorem is proven. So the theorem will be just essentially proven in two big steps and one small step. So the first step is to argue the following property. So imagine I have two disjoint set of sources. Let's maybe stick to that. S1 and S2. And suppose it so happens that I fix some subset of sinks T prime such that there is a linkage from S1 to T prime and a linkage from S2 to T prime. So maybe let me use a different color. And they end up in the same set of sinks T prime, and that they are both fairly big. Where big here means at least some function k, where k is the number of tripods we are trying to pack. Well, the conclusion shouldn't be surprising that in this case, we, I guess, morally should be able to argue that in the original picture, there's actually quite a lot of tripods. Where quite a lot means at least k. Okay. So that will be the first step. And to argue this, we'll need a tool called the onion harvesting lemma, which I will tell you more about in a bit. But I think this is fairly intuitive outcome. Like this is quite a rich structure already. All right. The second step is the, let's say, small step, is to invoke some matroid magic. And here, by matroid magic, I mean matroid intersection theorem of Edmonds. And what it will tell us is that whenever you have a partition of the sources into two sets, S1 and S2, you can always find a corresponding partition of the sinks, T1 and T2, and a small number of vertices you need to hit, such that there is no path that goes across. So there is no path that goes from S1 to T1, S2 to T1, not that avoids the yellow vertices, and likewise there is no path from S1 to T2 that avoids the yellow vertices. Okay. Again, I will tell you more about what exactly happens here at a later stage. And finally, use this statement as a small separation theorem. When here the idea is that if once I partition my sinks and sources, get the partition. Once I partition my sinks, get the corresponding partition of the. No, once I partition my sources, get the corresponding partition of the sinks. If I can pack at least one tripod here and at least one tripod here, that's perfect, because then I can apply induction separately on the bottom and on the top to get my conclusion. If there is no tripod here, no tripod here, then I'm done. The yellow set hits all tripods. So the only interesting case if there is no tripods in the top part and some tripods in the bottom part, but then I can try to move vertices from the top to the bottom. And what happens once I have the switch? Then I have two sets that should hit all the tripods. The yellow set from the step before the move, and the yellow set from the step after the move. So this is also fairly easy once we get the magic from the point 1 and point 2. Okay. So let's erase this part. So onion harvesting lemma. So there is this general issue in directed graphs that doesn't happen in the undirected world, and I will try to now explain it. So in an undirected graph G, if there's a large flow from X to Y, well, then this is the same as having a large flow from Y to X. And this is the same as having a large flow from X to Y and from Y to X of roughly half the size. Yes, I can treat half of the paths as going from X to Y and half of going from Y to X. However, this is not so in the directed world. So it is possible to have a directed graph, digraph D, and a pair of vertices xy, such that there is a large flow from X to Y, large flow from Y to X, but no simultaneous flow. Between them. Where by simultaneous flow I mean just a cycle on which they both lie, in this case. So how to construct such an example? Well, you start with a grid, and you direct all arcs to the right and to the bottom. Okay. Now you add two vertices. This is X, this is Y, and I attach X to every vertex here, and get attachment from every vertex here, and similarly to Y here. And as a final step, we split every vertex here into two, and the vertex of incoming edges and the vertex of outgoing edges. So a vertex here has an incoming edge from the left and from the right, and that edge, and we replace it with two vertices connected by an edge, one collecting the incoming edges and one sending the outgoing edges. And now I see a huge flow from X to Y that goes along vertex disjoint paths in this graph. So after the replacement, those are all edge disjoint. And I see a huge flow from Y to X going right through here. But once I send just one path from X to Y, I kill all paths from Y to X. And this is a very unpleasant thing if you try to do stuff like immersing graphs into directed graphs. But it turns out not to be hopeless. And this is where the onion harvesting lemma comes to the rescue. And it essentially, let's say, morally states that this is the only counterexample. Yes?
Just a question. Why do you want two flows which are edge disjoint, right?
Two flows. No, I just want a path from X to Y and a path from Y to X that are edge disjoint.
Why were these red additional arcs needed?
Because Otherwise, I simply take a path that goes like this and a path that goes like this. They meet in a vertex, but not in an edge. But once I do this replacement, they meet in an edge.
And you want them to meet in an edge?
Yeah, I want them to be. I want the simultaneous flow to be edge disjoint. Okay. So, this is theorem of Łukasz-Bożyk, Oskar Defrain, Karolina Okrasa, and Michał Pilipczuk. And it states the following: that there is a function g, say from natural numbers to natural numbers, such that for any directed graph D, any vertex of that directed graph, and any two flows, we take P, Q flows, so one of them is an outflow, so let's say start P X, where this means that all paths in P start at the vertex X. One is an inflow, Q, and this means that all paths in Q end in X, and they're both, let's say, of equal size, which is at least G of T, and they are pairwise intersecting. So for every path in the flow P and every path in the flow Q, some edge of P is an edge of Q as well. The conclusion then is that D contains an onion star immersion. Of order T. Center vertex. So what is an onion star immersion, you ask? Okay, maybe let's first tell you what an onion star is. So we have some center vertex here, and we have two T petals. And each top petal has got two arcs from the center vertex and one arc back. And each bottom vertex has got two arcs to the central vertex. And one arc back. And what is an immersion? Well, here an immersion is from, let's say, one directed graph D in is, let's say, B prime is an immersion. In D, if I can do the following. So I have my D, and I have my target digraph D prime. That looks maybe something like this. So in an immersion, I want to map each vertex to a different of D prime to a different vertex of D. And each edge of D prime, I want to map to a path of D in such a way that the paths are edge disjoint, not necessarily vertex disjoint. So for example, I can map it to a path like this. Yes, and this corresponds to this arc and this arc back. And this arc I can get going through again through this center vertex here. And so on. Yeah, let's go through this again. And with this notion in mind, it is not that hard to convince oneself that the T-onion star is an immersion universal graph for digraphs on at most T vertices and bounded in and out degree by 2 and total degree by 3. Which is the, if you think a bit more carefully about this example, it's exactly the case, what happens in this grid. Like I have at every vertex either 2 incoming arcs and 1 outgoing arc, or 2 outgoing arcs and 1 incoming arc, except for X and Y, but that's not super important. Do you have questions about the statement? Okay. So why is it useful for my setup? Well, the answer is because the tripod and onion are essentially the same thing. Except that once in a tripod I'm hiding the center vertex that I'm interested in. So let's start with the set of sources S, the same set of sources T, and we have some directed graphs, those and some other vertices. And let's add some extra vertex X here. And now connect every vertex in S via an in-arc going out of X. And every vertex in T by an edge towards X. And well, because what I was talking to you about was about vertex disjoint paths and not edge disjoint paths, I probably should also split every vertex in this picture into vertices with that collect the in edges and out edges. And now this tells me that vertex disjoint tripods in this picture become, in the original picture, become edge disjoint onions in the new picture centered at X. And edge disjoint onions, where onion is simply this bit of the onion star, gives me a vertex disjoint tripod in the original picture. Yes. So in particular, whenever I will find a flow terminating in T, linkage terminating in T, and a linkage starting in S that pairwise intersect and is sufficiently big, I can apply the onion harvesting lemma to conclude that I get my tripod packing. Okay. So I will write it as, and this will be important to derive the following lemma, which I call point 1 here. And let's call it the key lemma. So we have a digraph, distinguished set of sources and sinks. let's say that P, Q are linkages such that the say S to T linkages, the set of starting vertices of P is disjoint with the set of starting vertices of Q, but they end up in the common set. So end P let's call it T prime. And they're sufficiently big. So P Q is at least G key of K. So this is exactly this setup. The top linkage is the linkage P, the yellow linkage is the linkage Q, and our conclusion should be D contains K vertex disjoint triangles. Okay, so this has a proof. The proof is actually really simple. So let me take a vertex T of T prime. Well, there's a unique path in calligraphic P that ends in T, and a unique path in calligraphic Q that ends in T. Let's call them PT and QT respectively. So as the first step, let me define the following graph, directed graph, D prime, T prime, where I put an arc from T to S if and only if PT intersects QS, non-empty. So this is a graph with a directed graph with at least GK of K vertices. So by Ramsey theorem, I can find first either a subset of either an independent set or a tournament in this directed graph. If I get the independent set, of size at least K, well, this is a packing of K tripods that look like a letter V to turn on its side. Okay, so I get tournament. Well, and another Ramsey theoretic statement tells me that any tournament has a transitive subtournament. Yes, there's a fairly standard proof of this statement. Well, then let me take a group, a prefix of size 1/2 of this transitive subtournament, and a suffix of size let's say G from the onion harvesting lemma of K, and here we'll have G of onion harvesting lemma of K. But what does this definition tells me? This definition tells me that I have a set of paths P and a set of paths corresponding to these vertices from P and a set of paths corresponding to these vertices of Q that pairwise intersect. And now I can apply onion harvesting lemma to conclude that I have my packing of K tripods. So this cleaning here goes from I don't know what's happening to get two linkages that pairwise cross. and then the machinery of onion harvesting lemma applies. Any questions? Because you seem confused. So
this condition of edge from T to S is symmetric.
condition, no. Here I'm taking the path from P of T, and here I'm taking path of Q for S. So I have two paths, so it gives me a direction. Like I can have also an edge from S to T, but this tells me that the V of P ending at S intersects the Q ending at T. So this is not a symmetric condition. Yeah, I have two paths. They need not behave in the same way. But to apply onion harvesting lemma, I need to get them to pairwise intersect. And this is why I needed this transitive subtournament, because then I know that if I look at any edge, any path P ending at some vertex T here, and any path Q ending at some vertex S here, then they need to intersect because there is an edge from T to S. Okay. So then, onion harvesting lemma gives us backing. Excellent. So this actually leaves us in a very good spot to finish the proof almost. But now I need to tell you a bit about matroid magic. So, and here, so I will tell you the definition of a matroid, just to scare you a bit. So matroid M on universe U is a collection of families, a collection of sets U of subset of the universe, satisfying the following conditions. And these are called the independent set of the matroid. First is that the empty set should be an independent set. The second condition is that if I have a subset of an independent set, well, it better be independent. And the final condition is that if I have two independent sets, and one is smaller than the other, then I can extend the smaller one by an element of the bigger one. And make it still independent. So these are very interesting structures in and of themselves, but for us, the important bit is the theorem of perfect. Which tells us how to construct a class of matroids called gammoids. So we have a directed graph and set of sources and a set of sinks, and define I to be any subset T of big T, any subset of sinks such that there exists a linkage S to T prime that saturates T prime. So I can fully link T prime from S. This is a matroid. So in the context of this statement, it tells me that if I have two disjoint set of sources, and I look at the corresponding matroids on T, they don't have a common big independent set. And or rather, if they have a big independent set, big common independent set, then there's a backing of triangles. Why is this important? This is important because then we can apply something called the matroid intersection theorem of Edmonds, which tells us that if I have M1, M2 matroids on a common universe U, so they need to tell us something about the same subset of elements, then the size of the largest independent set that is independent in both matroids, 2, is the same as the minimum total rank of a partition. So I take the rank in the matroid M1 of X plus the rank of the universe minus X in M2. This is over all subsets of the universe, where given a set like this, rank of M of X is simply the largest size of an independent set that is contained in X. And yeah, you need to use 0.3 to show that this is a well-defined number, in the sense that you can take it pretty. So now, coming completely out of left field, we can see what will happen if we combine this theorem of Edmonds with the key lemma. So we get the following corollary. If we have S1 and S2 partition of S, then either 1, there are K disjoint tripods, or 2, there exists a partition T1, T2 of the set of sinks. There exists a set of vertices of our digraph, which is not too big, such that there is no Si to Tj path in D minus X, where I is not equal to J. So this is the picture here. The yellow vertices are the set X. We have some partition that we can take arbitrary partition of S1 of the sources into S1, S2. And the corollary tells us that there needs to be a partition of the set of sinks, where this partition is given here. And essentially, it just apply the Edmonds theorem. If we have a big independent set, well, what does the independence means? It means that this is a set that is linkable from S1 and S2, and then key lemma gives us K disjoint tripods. And if there's no such big independent set, then the right-hand side tells us that there is a partition of small rank. And what is rank? Well, by Menger's theorem, is the minimum number of vertices I need to remove to kill all connections. So I can apply Menger from S1 to T2 and get this number of vertices that I need to remove, and from S2 to T1 and get this number of vertices I need to remove. but their total number must be less than g of key lemma of k, because otherwise I would find my tripods. Okay. So this should be almost wrapping up. And I essentially told you the proof in the introduction. So we proceed to via induction on K. And let me denote by f of k is the number of vertices I need to remove to kill all tripods if there are no k vertex disjoint ones. So this is the function we need to define. Well, so the case of k equals 0, you can just set f of 0 to be 0. If there are no tripods, I have nothing to do. Okay, so inductive step. So we take our digraph D, set of sources, set of sinks, and we assume that there are no k tripods, k pairwise disjoint tripods. Well, then for all partitions S1 and S2, we apply the corollary to get the partition. Let's call this partition maybe S. So this is S1, S2, and a set XS, which kills all the cross connections we as on the picture above. Well, this gives me in a natural way two smaller instances. Let's call them DS1. Well, we take our digraph D minus the set XS. We take as sources S1 and sinks T1. So this is this top box in this picture. Well, actually, the instance includes the entire bottom box as well, but it shouldn't play much of a role. And that instance D2, let's take D minus XS as our host digraph. Sources are in S2 and sinks are in T2. And now the question we want to ask, does it contain any tripod? Well, if your answers are yes and yes, then I will tell you, excellent, because now I can conclude that the packing number of tripods for D1, let's make it calculate, of D1 must be less than k minus 1. The packing number, tripod packing number of D2 must also be less than k minus 1. Because any tripod, let's say from D1 of S, well, both sources need to be in S1, and it needs to terminate in a vertex of T1. Well, a tripod in S2 must have both sources in S2 and a sink in T2. Well, can they possibly intersect? Well, they cannot, because as soon as I see any intersection, I can immediately complete it to a path from S2 to T1 or from S1 to T2. And that contradicts the property that there are no such path after removal of the set X. And since I can pack at least one tripod in each box, and the total packing number of my starting digraph was less than k, by assumption here. Well, the packing number in those instances better be less than k minus 1. But this means that I can apply induction to kill all tripods here at the cost of fk minus 1, and here fk minus 1. So it would suffice to have fk at least twice fk minus 1 plus g of k, where g is the function from the corollary. Yes. Similarly, if you tell me no, well, a tripod in this picture must, that means that after removal of the yellow set, there are no more tripods in the picture. So again, I just need to have f of k is g of k. But this means that for every partition of the set of sources and sinks, we have exactly one no and one yes. So now let us call the empty side of this partition whichever part that does not contain any tripod. So in this case, it would be S1. Well, now let me just take a partition with empty side that is inclusion-wise maximal. Well, what does it mean? So I have this partition S1, S2, and without loss of generality, let me say that D1 S has no tripods. Oh, then S2, well, it could be empty, I guess, but in this case, that means that they have already killed all the tripods, or rather, there are no tripods in the picture already. So there is just nothing to do. Okay, so let me just take S from S2. And let me consider the partition S1 with added little s, and S2 without the little s. This is also a valid partition. And now, because I've chosen a partition with empty side maximal, this is no longer the empty side. This must be the empty side. So the claim is that, let's call this partition S prime, that XS union X S prime hits all tripods. Okay. And this is just nothing happening. A tripod with at least one leg in S1 is hit by XS. Because S1 is the empty side, so any tripod with a leg in S1 must end in T1 after removal of XS. But there are no tripods in the top box, so there are no such tripods. So this kills all with a source in S1, and this kills all tripods with a source in S2 minus the little s. But where can be the source of the tripod in the end? Well, it cannot be in S1. It cannot be in S2 minus S1, so it can be only in the little s. But the tripod needs two sources, and there's just one vertex. So this is the final contradiction. we just need fk to be at least twice g of k. And that ends the proof.
Again, YXS kills all tripods with just one source in S1. And
Yeah,
what
because
happens if you have one source in S1 and one in S2?
well, the point is that this set kills all connections from S1 to T2. So if my tripod contains a source from S1, it needs to end in T1. Well, the other source must now also be in S1, because otherwise it would be a path from S2 to T1. And now it must be a tripod in the top box, and I assumed that there are no tripods there. So that's the end of the proof of this theorem. I think it's like a super elegant proof in the end. Like once we cleaned all the details, it just falls out almost automatically from the onion harvesting lemma and the Edmonds matroid intersection theorem. And this is, well, this is all I would like to tell to you. This is all I have to say today. Unless you have any more questions, then I'm happy to answer them.